Hey everyone, and welcome back for part 2 of chapter 7 on sampling in Psych 3510. In part 1, we discussed the process of sampling in general, the distinction between populations, samples, and census. We discussed the sort of the process of sampling and then inference, and why that second step of inference is the really critical part of why sampling is an important thing to consider in your experiment. And then we ended with going over our biased or non-representative types of sampling. In this second part, which I think we've only got about 10 slides, we will go over representative sampling. Now, all of these sampling strategies are going to be based on probability or random, the introduction of randomness at some point. And then we're going to see that those offer us at least sort of some way to combat bias in our samples. So let's dive right in to our non-biased probability sampling techniques. We have simple random, clustering, and multistage. We're going to group those together because they're very similar. One sort of builds on the other. Stratified random sampling, oversampling, and systematic sampling. Okay, probability sampling is any type of sampling method where we just use something like a random number generator. So maybe we have access to 1,000 participants, and we truly, completely, and absolutely randomly select 50 of them, or randomly select 100 of them from whom to collect data. The researcher has nothing to do with this. You assign maybe every person a unique number from 1 to 1,000, and then you tell a computer to just choose X number of those numbers at random, and then that identifies your sample for you. So pretty straightforward. We like this because theoretically, the act of randomness sort of smooths over any biasing characteristics of the sample. So I'm just as likely to choose, let's say I'm studying something about personality. And we know that maybe personality is impacted by the parenting style of your parents. So I'm going to randomly select 100 Georgia State students. Some of them are going to have authoritarian parents. Some of them are going to have laissez-faire parents. Some of them are going to have authoritative parents. And their parents will have done things even within those categories in different ways. And by randomly sampling, the idea is that I will get a truly representative sample of all the different types of developmental parenting behaviors out there, because I'm just as likely to select someone from one of those categories as another category. And on the long haul, on the long arc of probability, everything will even out, right? So think of this as the roulette table of sampling methods. If you go sit down at a roulette table in a casino, that's the one with the red and green, the red and black, and then maybe usually they have two green little squares on a big wheel, and they spin the ball, and wherever the ball lands, you have to bet on the numbers on the table, and that's who wins. Over time, right, there will be an equal number of black numbers as red numbers. The issue with probability is that at any given stretch, it might not be perfectly even. So any given stretch of, let's say, 10 rolls, you might get 7 black and 3 red. You might get 8 black and 2 red. But then as we increase our sample size, as we roll the roulette ball, 100 times, 1,000 times, 10,000 times, it is going to get closer and closer to that true 50-50 of probability. So when we're using simple random sampling, we were confident that the randomness, evens things out over time. We just want to make sure we have a large enough sample size. If we're only sampling 10 people, just like with roulette, 10 rolls of the ball could give us anything. It could give us 10 reds. It could give us 10 blacks. It could give us 8-2. But then as we increase the number of rolls, we will approach the true probability with sort of more precision. So we like simple random sampling. We just need to make sure we have a large enough sample size. Okay. Next, we're going to talk about cluster and multi-stage sampling. First is cluster. We use cluster sampling when people in the population are already divided into somewhat arbitrary groups, and then we randomly select some of those groups and use all of the people in each group. So let me give you an example of that. Let's say you work for MARTA, right, or the city of Atlanta, and we want to understand commuter behavior. How do people commute in Atlanta? How far are they commuting from? What type of transportation? Are they carpooling? Right? What's going on? We want to understand commuter behavior for people who work in downtown Atlanta. Well, people are already divided into clusters in downtown Atlanta, mainly the building in which they work. Right? Let's say that's a cluster, or maybe the block upon which they work. And so what we do is we take advantage of these already existing clusters and we randomly choose 5 buildings in downtown Atlanta, right? So we identify every office building in downtown. We give it a number. Let's say there's 50 office buildings. So we have 1 through 50. We then randomly choose 5 of those office buildings, and then we collect data from everyone in the office building. So we're taking advantage of already existing clusters. We randomly choose a few of those clusters, and then we collect data from all of the people in each cluster. You often see this in educational psychology when people study schools. So let's say you work for DeKalb County Public Schools. We want to study second graders, right? Something about second graders. Well, we already have existing clusters. Those clusters are schools, right? There's, who knows, right? 30 elementary schools. Let's just say, I have no idea what the number is. Let's just say there's 30 elementary schools in DeKalb County. So I number them 1 to 30, and then I randomly select 3 of them. And then I collect data on all of the second graders in those schools. So again, we use this when people are already divided into clusters, and then we randomly select X number of those clusters, and we collect data from all of the people within each cluster. Multistage sampling takes cluster sampling. It doesn't change cluster sampling. It just adds a second layer of randomness. So if we continue with our building example, let's say that we randomly selected this building from downtown Atlanta. That's our first cluster. So, randomness number 1, this building was randomly selected from all the other buildings. And then within that building, we randomly select 100 people. Or we randomly select a floor, right? Floor number 6. And we sample the people from that floor. Multistage simply means you take cluster sampling and you add a second layer of random sampling below the first cluster. So we can think of these clusters as being organized in hierarchies. Right? You have a building, right? Within a building, you have floors. Maybe even within floors, you have sections of the floors, right? And so we're just applying random selection to at least 2 stages of that hierarchy. So we randomly select a building, and then we randomly select a floor, or we randomly select 100 people from within that building. To go back to our school example, we would randomly select a school, and And let's say that that school has 5 second grade classrooms. We would then randomly select 2 of those second grade classrooms. So we randomly selected the school, and then we randomly selected the classrooms. So cluster sampling plus an additional layer of random selection. Next, we have probably the only truly 100% way to get a fully representative sample, and that is stratified random sampling. Now, to do this, you have to be interested in sampling across a demographic category. We're going to use race here. A demographic category, and then you randomly select individuals within each of those categories proportionate to their membership in the actual population. So you have to have population level data. So if we're looking at race in America, then we would have to go to, this is actual data, I think from the last census. So it would be 2010 at the time of this filming was the last census. And along the right, sorry that my face is a little bit in the way here. Along the right, you see the exact percentage of the population in the United States of America that is from each of these racial categories. So, what that means is that as someone who is trying to perfectly mimic the racial makeup of America, let's say I wanted to collect data from 1,000 participants, I would need to collect data from 765 people who identify as white, 134 people who identify as Black or African American, 13 people who identify as American Indian or Alaskan Native, 59 people who identify as Asian, so on and so forth, right? So what we're doing is we are intentionally and purposefully selecting people such that our sample proportionately mimics the population on this given demographic variable. So you could use race, you could use ethnicity, you could use religion, you could use sexual orientation, all those sorts of things would be good candidates because we have lots of good data at the population level on exactly how many people are Catholic in the United States, exactly how many people are Muslim, exactly how many people are Jewish, right? We have a pretty good handle on that data from things like the census. So if we wanted to be critically sure that we have a representative sample on that variable, we could do stratified random sampling. The problem with stratified random sampling is that it becomes difficult when you include more than one demographic variable. So let's say that, okay, I want to use race, I want to use gender, and I want to use sexual orientation. So now I have to know, okay, of white people, exactly what percentage are male and female. It's going to be close to 50-50, but probably not exactly 50-50. What percentage are male or female? And then of males, what percentage are heterosexual? What percentage are homosexual? What percentage are asexual, right? However many of those category distinctions I want to have. So now I have the category white, male, heterosexual, white, male, homosexual, white, male, asexual. Right? So suddenly things get a little more complicated because I need to know exactly what percentage of the population each of those groups of people is. And then I have to do white, female, heterosexual, white, female, homosexual, white, female, asexual. And that's just white people. Then I have to move on to Black or African American and do the same thing. American Indian or Alaskan Native and do the same thing. So you can see that it becomes unbelievably complicated to do this if you have really more than one demographic variable that you're interested in sampling along. So generally when you see this done, it's only going to be done with a single demographic variable. Now, our next non-biased sampling method is called oversampling. Now, this combines elements of stratified random and something we learned about in part one, which I said we'd bring back, quota sampling. So oversampling is a version of stratified random sampling where we intentionally choose to overrepresent a group that is such a small percentage of the population that if we followed if we followed the exact representative percentage, there would not be enough of those people from which to draw valid conclusions. So again, let's say I want to sample 1,000 U.S. residents. If I did 1,000, right, we move the decimal point to the right to tell us how many people we need. We would only sample two Native Hawaiians or Pacific Islanders. That's not enough data to draw conclusions about that group, right? 2 people in that group will tell us nothing about the overall attitudes or behavior of that group, right? We would not want to make an inference, right? We would not want to draw a conclusion about all Native Hawaiian and Pacific Islanders after only collecting data from 2 people in that group. That would be ridiculous, right? We would never think about, drawing a conclusion about all women from 2 women or drawing a conclusion about all men from 2 men. So we shouldn't do it when it comes to Native Hawaiian or Pacific Islanders. And so oversampling is the process by which, for the major, in this case, racial groups, so we would probably white, black, Asian is probably enough, and you can't see the Hispanic or Latino, but that's a high enough percentage where we would be okay with those proportional numbers. But then we're going to intentionally bump up the numbers of Native Hawaiian Pacific Islanders, and we would probably intentionally bump up the numbers of American Indian or Alaskan Natives, because collecting data from 2 people and 13 people in a particular group is just not enough people. So we do stratified random sampling for the majority groups, and then below some threshold of proportion, we intentionally oversample. And let's say we bump up the American Indian and the Native Hawaiian numbers to like 50, right? Just to get to some reasonable number where we would be a little more confident about making an inference from that number of people. So we do stratified random for the majority groups, and then we intentionally oversample from minority groups. Okay, and one of our last non-biased sampling techniques is called systematic sampling. This is where you don't necessarily have like 1,000 people and then you randomly choose 100 of them. What we're going to do is use a random number generator to select 2 random numbers. Let's say it selects 40 and 21. And let's say we have this stadium of people. We would start at seat 40, right? Because that was our first number. Say that's here. And then we would ask every 21st person to be in the study. You'll often see this in naturalistic settings, like a stadium, or maybe political polling, like out on the street or something like that, where you would say, okay, I'm going to start with, I'm going to generate 2 random numbers. I'm going to stand on the street corner, and starting at number 17, because that was the first number. So the 17th person that walks by, I'm going to ask them to be a part of the study. And then let's say the next number was 9, every 9th person after that, so 1, 2, 3, 4, 5, 6, 7, 8, 9th person, I ask them if they want to be a part of the study. It's just a way, often in naturalistic settings, to develop some randomness to who you ask. Because notice how this is subtly different from simple random. Simple random sampling would be like, I have all, whatever, 50,000 Georgia State students, and I know who they are, and I have their contact info, and then I randomly select 100 of them. That's different because I I have this defined population, and I'm capable of contacting anyone in that population that I might need to. In systematic sampling, we're typically out in the world. We're in a naturalistic setting, a street corner, a grocery store, a soccer stadium. And so we don't have the ability to contact these people at random, right? That's not going to happen. And so this systematic system enables us to randomly select people maybe for whom we can't just contact out of the blue, right? They're just passing us on a street corner. And so it allows us to imbibe some randomness into that process. So the key takeaway here is that what makes our non-biased samples good, what makes them non-biased, is the inclusion of some element of randomness. Randomness is the great equalizer. Even if you are forced to engage in a biased sampling method, you want to look for places where you can insert randomness if possible. Because if you can insert any amount of randomness, it's going to increase the external validity of your study that you use that sampling method for. So we like randomness. We want randomness. We want as much of it as possible, even if we have to make consolations elsewhere with our sampling methods. In particular, randomness is a extremely high priority. And so having an unbiased sample is extremely high priority for frequency claims. Frequency claims, if you remember, are things like 4 out of 10 women are unhappy with their employer. Right? It's a single statement about a single variable. 29% of drug addicts attempt suicide. Half of toddlers are at risk of daycare injury. These are claims about a proportion, a percentage of a single variable. Frequency claims need randomness in their sampling methods because what these claims generally do is make large inferences about large groups of people. And so it's incredibly important for frequency claims to have external validity. So some kind of randomness in a non-biased sample is a high priority for these claims because we're making a claim about all women. That's an enormous, I mean, that's billions of people. Drug addicts, that's millions of people. Toddlers, that's millions of people. To make such a giant claim, such a giant inference, necessitates external validity because the purpose of these claims is to apply broadly to tons of people. And so if we don't have external validity, then frequency claims become extremely, extremely weak. Now, we like external validity in our other claims, in our correlational claims and in our causal claims. But in particular, for frequency claims, external validity is a must. And so we want to, with our last point here, we want to sort of we want to deal with an often troublesome issue in sampling, which is sample size. The general rule of thumb is that the more data, the better, right? Why not? 1,000 data points is better than 100 data points, and 10,000 data points is better than 1,000 data points. So in general, that's a good rule of thumb. More data is better. But there is a point at which we see diminishing returns for those larger samples. So it's not necessarily the case that larger samples are more representative than smaller samples. You would rather have a well sampled, slightly smaller sample, a unbiased small sample, than a terribly biased large sample, right? If your data are biased, it doesn't matter whether there's 50 or 50,000 people. The data are biased, and so will your conclusions be. But we do want to have as large of sample sizes as possible while still maintaining representation in our sampling methods. But once we really get above the world of like 500 participants, we see diminishing return in sort of the margin of error of the experiment. So, if I think this example is just taken from political polls. So, when a political poll only has 50 people, it'll have a margin of error around 10%. That's enormous, right? Because that's the difference between, 50% of people supporting your candidate and 40% of people supporting your candidate. It's a massive shift, right? That's the difference between a really close election and a blowout election. So as we move up in sample size, we can see that our margin of error goes down because as we have more people, in general, we're more representative, and in general, we're going to be more accurate, provided we have good sampling methods. But once we get above 500 or 1,000 randomly sampled people, we only get small incremental decreases in margin of error. Remember, a decrease in margin of error is good because that means we're honing in on the truth, right? Our margin for error is small. And so you'll often see political polls that have margins of error around this 3 to 4% because it's not really worth the time and the effort and the money to go from 1,000 to 2,000 participants, right? We're going to double our sample size only to reduce margin of error from 3% to 2%, right? So it's a rather trivial reduction in margin of error, but it doubles the cost of our survey, right? It doubles the time and expenses. And so the trade-off just isn't quite there. So in general, we're looking for samples of around 500 is a good place to be in these kind of surveys. Around 500 with unbiased representative sampling methods will give us an acceptable margin of error without overburdening the study itself. Okay, well, that's it for part 2 of chapter 7 on sampling. Thanks everybody for listening, and I will see you next time.